In this video, we will explain how Einstein applied quantum principles to light and the wave-particle duality problem that emerged from his work. In Newton's time, light was thought to be made out of particle-like objects. He used the nature of straight-line shadows to inform these ideas. If you shone a torch through two slits next to each other and light acted like a particle, you'd expect two beams to pass through the holes in a straight line like this. Thomas Young tried this experiment a century after Newton. He found that light acted like a wave instead of a particle. After going through the slits, the waves diffracted outwards and interfered with each other. This created these interference lines where the waves reinforced each other, which is very different from how the light would behave if it was a particle, where it would just flow through the red beams highlighted. The pattern shows interference with light and dark fringes where the two waves interfered. A century later is where Einstein came in and tried something new. He shone a light at a metal surface and measured the current. This was the photoelectric effect. The light would give energy to electrons that would escape and create a current as they flowed. He expected that as the light got more intense, the current would increase. And as the light changed colour, which was a change in the frequency of the wave, the current would pretty much stay the same. But he found that once the light reached a low enough frequency, the current completely stopped altogether. Even as he increased the intensity of the low frequency light, no electrons were ever freed and no current was ever formed. This didn't add up. According to wave theory, when the light hits the electron, it continuously delivers energy until the electron has enough energy to escape. This energy amount is called the work function. So, no matter what frequency the light was, eventually it would build up enough to free the electron. To solve this puzzle, Einstein thought back to Planck's ideas. Planck originally proposed that if an electromagnetic wave hit a mass spring oscillator, the energy could only increase in discrete steps instead of continuously. Furthermore, the step size of the energy changed depending on the frequency of the wave that was supplying the energy, as we covered in the previous video. Einstein adjusted the idea to say, what if it's not the energy exchange that occurs in discrete steps, but instead the actual EM wave hitting the particle is delivering the energy in discrete steps, in packets of energy called photons that have an energy equal to hf, Planck's constant, multiplied by the frequency of the wave. When applying this idea to the photoelectric effect, it explained the behaviour perfectly. The energy delivered in photons would excite the electron, but if the frequency of the light was not high enough, there would not be enough energy per photon, and the electron would not overcome the work function to escape. Whereas, if the light was at a higher frequency, the photon would excite the electron enough for it to escape, and give it some kinetic energy as well. So that explains how Einstein formulated the evidence for the particle-like nature of light using photons, and this is where the wave-particle duality comes into play. We have evidence from Einstein's photoelectric effect that light acts like a particle, and evidence from Young's double-slit experiment that it acts like a wave. Physicists had to figure out how to make sense of this wave-particle duality in the nature of light. Before tying up this loose end, in the next video we will go into how Niels Bohr applied quantum principles to the atom. Thanks for watching this one, and I'll see you in the next.